Hello, I'm Elias Safra. I'm an associate professor of computer science in Clemson University. Soon we'll be moving to the University of Delaware. So, in this part of our tutorial, we would like to share with you our experience on how to use the existing NISC devices for solving large-scale combinatorial optimization problems. Um, I'm sure that you know that there exists 10, if not hundreds, of different classes of algorithms for large-scale combinatorial optimization problems. Some of them are more practical than others for certain classes of problems. Some families of algorithms admit effective parallelization on different types of high-performance computing architectures, and many of them rely on the heuristics to prune the search space, which of course accelerates the solver. And many algorithms and strategies are based on different types of relaxation techniques of integer constraints with then subsequent return to the integers by using different types of rounding schemes and others. But despite of their effectiveness and availability of computational resources and parallelization methods, there are always certain barriers in the problem size and the algorithm complexity, which is especially sensitive if not much is known about the instance structure or a special case of the problem that we solve. And when these barriers are met, then the typical ways to tackle the optimization problem is by using different types of decomposition and local search methods. And in many algorithmic frameworks, these methods are iterative, which means that they work until a reasonable solution or some computational limit, for example, in time, is achieved. So in the decomposition method, we look at the domain and we can break the problem into parts, right? And then we'll solve the problem, or as we call it, sub-problems in different parts, and then we'll combine the solution. In the local search method, we will start with some initialization, and we'll explore some neighborhood of the solutions for the problem, and then we'll progress and we'll hopefully improve the solution. But the problem is that both methods, and by the way, there are some, in many frameworks, the decomposition and local search methods are combined with each other. But the problem is that both families of methods are often blind with respect to some boundary conditions. In other words, the problem is solved for a certain number of variables while making other variables invariant. So for example, if we solve a sub-problem in this part of the domain, then we may not necessarily know what happens with the variables and with the interactions between variables in other domains, right? So we fix the boundary condition and solve something, solve the problem in this specific area. But with these two approaches, we still have another barrier, and that barrier is sometimes not less important, but even more important than others. And the barrier is that we normally solve in all these methods one variable at a time. And when I say one variable at a time, it's not necessarily one variable. It's more precisely, we can say that we solve a limited, very limited number of variables at a time. The class of methods I would like to discuss and show its application in hybridization with NISC devices makes an attempt to resolve this problem. If our strategy is to map a classical variable to a qubit, which is what happens in the vast majority of approaches, like, for example, QUBE formulation, these devices, they represent a major obstacle. They're unlikely to handle enough qubits in the near future to tackle practically interesting optimization problems directly. So the question in this part of the tutorial is how to utilize them efficiently. And the class of algorithms that we're going to discuss provides a framework that will effectively utilize the NISQ devices. And the interesting thing is that in the same time, this specific class of algorithms, the multi-level algorithm, will in turn benefit from NISQ devices as well. So now let's talk a little bit about the local search strategy. The simplest algorithms, or in some cases they're called unstructured methods, they use a strategy of generating and testing the solution without any use of prior results to guide future choices along the search path. The so-called structured approach to the search builds solutions incrementally from smaller parts. These methods exploit the fact that in many problems, the small parts can be tested for consistency before they are expanded to larger ones. And this allows very effective early pruning or backtracking in the search space. Now, the second approach that is actually used in the local search is taking advantage of the clustering of solutions. And this can be found in many applications, in many search problems. So in other words, instead of being randomly distributed throughout the search space, the states have a neighborhood relationship such that the states with fewer or null conflicts, in other words, with the similarity of the solutions, they tend to be near other such states. And this neighborhood relationship is used to choose the next step in the local search. Now, the problem is that such searches can become stuck in local minima very easily, but often they are very effective. The local searches, they operate in a smaller search space. They normally don't consider the very small parts of the problem that are used for early pruning or backtracking. And the problem is that on the other hand, they also disregard any information from these small parts that can help them to choose the next solution along this path. So classical version of local search, of this repair style search, consists of selecting a solution at the initial state and then repeatedly moving to another state, which is a neighboring state to the current one. And this is repeated until a solution is found or the number of search steps reaches a certain bound. So it normally depends on the availability of computational resources. So the two key ingredients of such local search algorithms are identifying the neighboring states, which requires some sort of notion of the similarity between solutions, and then selecting the mechanism to select from among these neighbors the next one to use. Now, in the quantum search, the situation is different, right? The quantum search operates on the superpositions of all solutions. Instead of selecting only a single new state, each step of the algorithm considers all possible new states. This parallelism offers the possibility of improving local performance by arranging for interference among many different classical search paths. Right, so that's the difference between the quantum search and a lot of strategies that are inspired by Shor and Grover's algorithms and the classical local search. So, so the classical case operates on a limited number of variables change over time. The quantum search operates on the superpositions of all solutions. Okay, so there exist many different strategies in both classes. Of course, the classical case is much bigger. The examples include algorithms like simulated annealing, taboo search, or evolutionary search, genetic algorithms. So we're going to discuss how do we hybridize the classical local search and use the NISC devices effectively, and how do we overcome this barrier of the classical local search and operate not on the limited number of variables that are changed at a time, but on many variables in one step. So here's an example of a typical behavior of a local search in some combinatorial optimization problem. In this case, it is a maximization problem, so which means that we need to maximize the objective. And let's say that we don't know anything about the structure of the problem. A typical behavior of a local search that is applied by iteration is to start from some random guess, and then we don't know exactly what is the quality of the objective. And then we applied several steps of this iterative local search. We improved the objective, and then we enter into the area of slow improvement. So we actually improve the solution, but not by a lot. And then at some point, we get stuck in some local minimum. And then maybe we'll change the algorithm and use another type of local search that operates on a different criteria. And then it will help us to escape this local attraction basin in this area, and we'll improve it. And then again, enter into the slow improvement zone. And then again and again, we'll switch the algorithm at some point. We won't be able to improve it anymore. This strategy normally takes lots of iteration steps, and they're normally slow, which actually motivates the use of multi-level strategy that we're going to discuss. So let me tell you a couple of words about the multi-level or multi-scale algorithms, because they're very general. They're not only about the hybridization of quantum and classical methods. They're widely used in computational optimization, in numerical methods. So let's look at a couple of motivating examples. Let's look at this painting. Right. And when we need to describe what we see in this painting, we really need to address this question at multiple scales of coarseness, or at multiple resolutions, right? Because when we increase the resolution, right here we see the face here. When we increase the resolution, we can see the horse, right? We can see the Don Quixote. If we increase the resolution even more, then we can see these weird faces. So in other words, when we need to answer the question, what do we see here, we need to operate at different scales of coarseness. Another motivation for the multi-level or multi-scale algorithms is the fact that the elementary parts of the system that we're going to optimize, they may exhibit complex and even non-deterministic behavior. So we don't know exactly what laws describe their interactions, for example. So let's look at this social network, right? And if we try to describe the relationship between actors in this social network, it could be a really difficult question. Now, the ensembles of them or the clusters of them can be much more structured, and they can help us to approximate the problem at the finer scale if we know how to solve the problem at the coarse scale. So in multi-level algorithm, we use the following structure. We start with a problem at the finest level. Let's say we have a problem with lots of variables. In general, these methods are used on very large scale problems with millions, billions, and trillions of variables. And then with the process that is called coarsening, we create a hierarchy of restriction operators that help us to compress the problem and make it smaller. So let's say that we have n variables at the finest level, and we have some operator that is used to compress this problem. And let's say we compress n variables into n over 2, and then we continue to apply this restriction operator, and we compress the problem all the way from the n variables level to some small level that we can solve effectively. And let's say we have here at this level only 100 variables. So we solve the problem exactly, the optimization problem exactly. And then with the process that is called uncoarsening, we start to lift up the solution obtained at the coarsest level, scale by scale, all the way back to the original level by interpolating it from the coarse to the next finer level, and then refining it at each level. Now, if our coarsening is a linear time, if it is fast, and if the uncoarsening is fast, which is normally achieved by solving local small sub-problems that refine the solution, then the complexity of the entire V-cycle, so this cycle, this algorithmic scheme is called the V-cycle, is linear, and the entire strategy is very fast. Now, this V-cycle is not a unique scheme for a multi-level approach. There exists other cycles that are called W-cycle, when you can revise levels using different scheduling schemes, so you can coarsen, then uncoarsen, and then you can use this solution to coarsen it again, but more correctly, and then you uncoarsen it again, and then at this level, you use this solution at this level to coarsen it again. And there's another scheme that is inspired by multigrid. It's called full multigrid scheme, or F cycles, in many combinatorial optimization problems. So this strategy, the strategy of cycles, which can be repeated iteratively, was coined in 1960s, and it was started with lots of different approaches that are called multigrid in the numerical analysis and scientific computing, and later they were used in the computational optimization. Now, there exists a variety of different multi-level, multi-scale algorithms, so different people call them different names, it depends on the field of science that are used, this strategy. So people use multi-grid inspired strategy in convex optimization, and in PDE constrained optimization, and trust region methods, in derivative-free optimizations. These methods are really successful in many different types of NP-hard optimization problems. There are many different methods developed for hypergraph and graph partitioning and clustering, variety of methods for graph and matrix arrangement problem, like minimal linear arrangement, bandwidth, work bound, minimization of matrix fill-in, and so on, vertex separators, coloring, traveling salesman problem. There's a whole class of algorithms to optimize VLSI placement. So all these algorithms, they follow the same cycling schemes, iterative cycling scheme, and use the coarse levels to approximate the solution at the finest level. So we're going to discuss a couple of problems. I'm going to demonstrate a couple of problems and a hybridization of multi-level, of a classical multi-level driving routine, and calls for NISC devices to get a solution of a small problem. So the first problem that I will show the results and the coarsening scheme for is called the graph partitioning problem. This is a classical NP-hard optimization problem. The goal is to split the set of nodes into k parts. Like in this example, we have 3 parts. And the constraints are that the size of each part, the number of nodes at each part, is approximately the same. There exists, we normally talk about some imbalance factor alpha that allows one of these parts to be bigger than another. And the objective is to minimize, if the graph is unweighted, then the objective is to minimize the number of edges that span more than one part, like these red edges, right? Or if the graph is weighted, then we minimize the total number of weights of these edges that belong to the cut. There exist many different graph partitioning algorithms that are multi-level, and I just wanted to show you a snapshot of a famous graph partitioning benchmark for exists probably 20 or even more years. And in yellow, you can see the algorithms that are actually either fully multi-level or they were applied in part using the multi-level strategy. So they use the multi-level strategy as the initialization and then improved with some refinement. So the second problem is the network community detection problem. It's also known as graph clustering, and this specific version is called the modularity maximization problem. The modularity is the quality metric to detect the community structure in a network. The problem is really similar to the graph partitioning problem. In fact, in our paper, we show how to translate one problem into another. It's not that difficult. So the goal here is to maximize this quantity, which is the difference between the actual number of edges in the community and the expected number of edges in the random model. So here we use this A as the adjacency matrix of a graph, and Ki and Kj are the degrees of node I and j respectively. So this is an expectation for the number of edges in the random graph. And the binary variables are the community assignment variables. So -1 points to this, say, the red community, and +1 points to the blue community. All right, so this is also well-known NP-hard optimization problem with lots of different algorithms, and some of the famous algorithms are multi-level algorithms. So let's start with the quantum local search strategy. And the quantum local search strategy is inspired by the classical local search. So what happens is in this strategy is that we use all the good things that we have in the classical computers, like large memory. We can store the global problem, we can perform the problem decomposition, and each small sub-problem in this local search will be solved at the NISC device. And the idea is that even if the NISC devices are currently not extremely effective and we cannot demonstrate the real quantum advantage NIST devices in comparison to classical devices, then hopefully in future when they will be noiseless or almost noiseless and they can be utilized effectively, then this driving routine used on the classical device can call for solving small sub-problems at the NIST devices. There exists lots and lots of different approaches applied on many different architectures, on gate-based architectures, on quantum annealing architecture. So here's a few recent examples for solving the community detection problem, scheduling problems, portfolio optimization, vehicle routing, and so on. Okay, good. So we have tried to apply this local search strategies, local search hybrid strategy on the community detection problem. So in other words, what happens, we have some solution of the community detection problem. It's just an initial guess. It could be a random guess. And then at each step, we selected a sub-problem that we want to optimize. The nodes that we want to optimize here are in yellow. The rest of the variables, so the assignments of the rest of the nodes, red and blue, are fixed, right? They remain invariant. Then we formulate this small sub-problem, send it to the NIST device, get the solution, right? We use it on both. We've tried to use both gate-based devices of D-Wave, of the IBM, and the quantum annealing device of D-Wave. And then we get the solution back, incorporate it in the global solution, and continue with this process until it is converged. So this is also a classical iterated local search approach, right? The difference is only when we use the quantum device for it. Now, the results were quite surprising because we've reached the optimal solutions. So here you can see that we compare the global solution, right? We use problems that we were able to solve exactly. And we compare here the IBM QAA approach and the quantum annealing used on the D-Wave device. And in the blue, you can see exactly the same local search approach, but instead of calling quantum device, we call the GUROBI, the classical optimization solver. And you can see that they're really comparable with each other, right? So there is no, there's no particular winner here. They all reach the global optimum. The spread of the solutions is approximately the same in all of them. And the number of iterations that are required for convergence is also not that different. So all these motivated us, why not to try, if the local search, this hybrid quantum local search is successful enough, why not to try it with the multi-level strategy, and why not to try to increase the size of the problem and scale up this algorithm in general. So let's talk a little bit about the coarsening strategies, because this is the key strategy for, because this is the key question to design a good algorithm and multi-level scheme. So a very simple coarsening strategy that you can find in a bunch of different multi-level solvers for graph partitioning and reordering would be just taking a couple of nodes, merging them, and continuing coarsening them in this way when we merge a couple pairs of nodes, solving the problem at the coarsest level, right? And then returning the solution all the way back to the finest level. How do we explain it? 2 or more vertices are merged. So in other words, we create from a pair of nodes like these 1 and 3 a coarse variable 1, 3. We merge them if they have a good chance to interpolate the solution from one variable to another. Another way, if they share some common properties. So for the partitioning, the common property will be belonging to the same part. If we solve the linear arrangement problem, then the property would be that the location of node I in the final arrangement would not be that far from the location of node J, and they can reinforce each other and help to interpolate a solution from one node to another. So the problem with this approach is that we make a local decision before we accumulate enough global information about the problem. So when we design a multi-level algorithm, there are 4 main questions that we need to address. The first question is, what is the distance metric between the nodes or between the variables? In other words, based on what criteria and based on what kernelization we can couple the variables. So in general case, it's not necessarily coupling. I will show you a more general strategy, right? But for the most simplest approaches, we just merge pairs of variables. And then the question would be how to find the find to coarse operator, how do we compress, how do we decompress the problem, and how do we refine a problem, right? So the first question is, how do we find the distance metric between nodes? And there exists lots of approaches. Many of them are inherited from the algebraic multigrid, and you can see a bunch of references here. So we use so-called the algebraic distance between nodes. The algebraic distance between nodes is the distance between the corresponding entries in the vector that we use in iterator matrix to relax the initial guess. So the stationary iterative relaxation matrices that we used, like Gauss-Seidel, like Jacobi successive over-relaxation and Jacobi over-relaxation. So here they're represented using the iterative form. That's the diagonal part of the graph Laplacian. This is the lower triangular part. This is the upper triangular part of the Laplacian. And each iterator is used in this form. So the iterator matrix times some vector values per node, and the next iteration would be would look like this. Now, we use, the algorithm is to use several steps of stationary iterative relaxations, and then the distance between the nodes will be measured by the distance between the relaxed values. And we can use our random initializations. So in other words, we can do this in R-dimensional space, and we can do this k iterations where k is not that large. So here, let me show you a very simple example. Here's the graph, and here's the diagonal. In this graph, we start this iterative process with the random assignment of all nodes in the two-dimensional space. So we drop all these nodes randomly in two-dimensional space, and you can see this red diagonal here. And then if we run, say, Jacobi over relaxation for just maybe 10 iterations, we can see that the length, the distance between these two nodes is longer than the distance for the rest of the nodes. So what it does, it helps us to distinguish between so-called global edges, or the edges that connect distant regions in the network that they are not similar to each other, and the regions that are more local. All right, so this function, this algebraic distance will be our distance between the variables that we're going to coarsen. Now, this process, you can see in the paper, in our papers, that this process is slowly converged, but it stabilizes very quickly, which means that we can use it in the multi-level framework, and we don't need to use lots of iterations to relax it. So that framework would be really fast. So I refer you to look at the details in all these papers. So now when we know the distance metric between nodes, we need to find define to coarse compression operators. And there are several types of this operator. In the first simplest type of operator used in many different approaches, including hierarchical coarsening in various machine learning frameworks, is the iterative selection of some variables and passing them to the coarse level. So here we select some variables. We say that these variables will go to the coarse level, and the solution for the rest of them will be interpolated from this smaller problem here. Then the second strategy is a little bit better. We merge pairs of nodes based on some criterion, for example, based on algebraic distance or another smart distance function, and connect them, move all of them to the coarse level, and this forms our coarse problem. And then the solution of each of these coarse nodes will go back to these variables, and then they will be refined. Now we're going to use a strategy that generalizes both iterative selection of some variables and the strict coarsening. We're going to use the algebraic multi-grid, algebraic distance-based coarsening of a graph Laplacian. So in this strategy, we start to select the coarse variables by choosing the most representative nodes. We're going to go through the details in the next slide. Then we will grow aggregates around these seeds, allow intersection between them, and that will form our coarse problem. So how do we do this algorithmically? We start with selecting the most representative nodes. It's a dominating set of nodes in a such way that all nodes that are not these seeds, they are strongly coupled to the chosen seeds. And strongly coupled means some kernel-based coupling or using the algebraic distances. So the strands of the connection, relative strands of the connection, is really the algebraic distance. So say the algebraic distances for these two edges are strong, and for this one is not strong. So this node is strongly connected to those that are already chosen to be in a set of seeds. And then with that in mind, we define the interpolation weights of all nodes or all fine nodes that are not the seeds. All right, and with that, we form the quadratic form for the coarsening. So if this is the fine level graph Laplacian, so the negative weights are of the edges are in the entries where the edges are present, then zero otherwise. If there is no edge, say between A and B, there's a zero, and the total weight of the adjacent edges are on the diagonal. Then the restriction operator that will be used in our quadratic form looks as follows. So this is the matrix of coarse level vertices by the fine level vertices. And the entry in this matrix says the following. So how strongly this fine level node J belongs to the coarse level node I. All right, so then we create this quadratic form, and the form will give us, except the diagonal, it will give us the coarse graph Laplacian. That's it. So that's the coarsening procedure that we use. As simple as you see. If the coarse graph Laplacian is too dense, then we can sparsify it with different types of graph sparsification strategies. It would not affect that much the solution. So we're done with this part. And so far, this strategy is used on the main driving routine, and no quantum computing use was in this part, right? So far, we're just coarsening the process, coarsening the scheme. But now, when we get a problem that is small enough, let's say with several variables, right? I don't know, 20 variables, 25 variables, or 30 variables, we need to solve the problem exactly. And at this stage, we can start using the quantum computing. We can start to apply the NISQ device. Now, the next stage would be coarsening, coarse to fine operator, and then there will be a refinement operator. So the coarse to fine operator, the decompression operator, is also inherited from the algebraic multigrid and other multi-level strategies. The refinement operator, in which we'll split the problem into sub-problems and locally refine them, locally improve them, would also be quantum. Now, what is the goal of the entire strategy? And why do we think that NISQ devices can be helpful here? If we solve a small problem at the coarse level better with a quantum device than what we can solve with the regular device, and it does not happen now, it doesn't necessarily happen now, but it will hopefully happen in future, then a better solution at the coarse level when the fine level variables are aggregated, it will imply a better solution, a significantly better solution, or significantly better improvement at the finest level. Because unlike in the classical local search, at the coarse levels, we don't operate in the mode of one variable at a time. We operate on groups of variables. And that's what helps, that's precisely what makes the multi-level frameworks so attractive. So, for example, in the graph partitioning, when we have a solution of the coarse level, we project the solution back to the original nodes, decompress the problem, and then with the refinement, we slightly change the solution that was inherited from the coarse level. If we refine a problem better, then we can expect much larger change at the finest level. So that's our general hybrid quantum classical multi-level approach. These are the places where we use calls for NISQ devices. All right, so let me show you some results of the quantum multi-level local search, and these are the results using the calls for IBM Q-gated device and the D-Wave. Now, first of all, the graphs that we solve with this approach, they're relatively large. Of course, multi-level device, classical multi-level algorithms, they are able to solve graphs with billions of nodes, right? But current calls for quantum devices are limited, right? So these are the sizes of a graph that are also relatively large already for getting more or less, for being more or less interesting. So here we solve the modularity problem, and this line represents the best known solution so far. We cannot solve the problem exactly. I mean, no global optimization problem will solve the problem for this size, but we can use the best known solution. And we can see that in many cases, we do reach this best known solution with our hybrid quantum classical multi-level scheme. So these are the graphs. You can see the sizes of the graphs. And what you see here is the ratio between the best known and our algorithm. And that's the right, and that's the line that shows the best known solution. So we have tried to tackle this problem with different subproblem sizes on D-Wave with 20 variables, 64 variables. We've tried to apply Kahib, which is one of the best multi-level solvers for classical solvers for graph partitioning. In fact, we used its coarsening strategy. We have tried to apply to compare with the classical optimization solvers for subproblems of size 20 and 64, and we used QAA to solve the subproblem of size 20. Unfortunately, we cannot. Or in the time of writing the paper, we were not able to move to the size of 64, right? So we used the real IBM Q device with QAA, and we used the QAA simulator for the size 20, and we compared it with spectral approach and with fluid communities. So you can see that in both cases, in D-Wave case and in QAA applied on IBM Q device, we can reach the best known solution. And here we can see the number of iterations, number of calls required for these devices that they're not large at all, and they're comparable with the classical multi-level calls. So here we ask another interesting question. Let's pretend that the problem size will be growing, right? And let's say that the hardware size will also be growing. What can we expect from this device? Can we expect a better performance? And here in this plot, we show the dependence between the hardware size, right, that will eventually grow at this point, say from 0 to 100, and the approximation ratio, all right, on some instances. And you can see that if we use this approach and the hardware size is growing, then we can expect a higher quality solution, right? Whereas the standard deviation for the solution with increasing hardware size will be smaller and smaller. Okay, what about graph partitioning? Graph partitioning is now also not that far from the modularity optimization. So we use the same framework, but the objective was now to solve the graph partitioning. The graphs are also relatively large, and we use the same setting of solving subproblems of size 20 and 64 in the D-Wave devices, and we experimented with only a subproblem of size 20 on QAA, and you can see that we can reach, in many cases, quite good and acceptable solution. The quality is a little bit worse than in the modularity case, but still we can reach quite acceptable quality, and the number of iterations is not that large. All right, so with that, I would like to conclude my this part of the tutorial. So we presented a way to hybridize quantum and classical devices in the multi-level framework. And we hope that with the development of these devices, with the next improvements to reduce the noise, decrease the number of shots that we need to use in this these devices, we hope that this is the one of the most correct and plausible ways to hybridize classical and small NIST devices for solving practical large-scale optimization problems. So these strategies summarized in this paper. You can find the benchmarks, the code there, and try this strategy by yourself. Thank you.